Welcome to Web Handling. My name is Dave Roisum. This is a continuation of a mini-series on measurement. The theme of this series is that measurements are not nearly so straightforward and trustworthy as you might think. In this clip, I recall a horror story on a common strength test measurement. However, this story is not a one-off. It reflects 100 other instances which I've personally worked on where instrumentation and test results were proven demonstrably, simply not trustworthy. I know your time is precious, so let's get started. Recall from the last clip the Roisum rule of instrumentation. That is, the more expensive it is, the less I trust it. It has a corollary. I don't even trust tape measures and T-squares. We'll add to this list in this clip with one of the most common measurements in the web industries, tensile strength. The strip tensile strength is one of the three most common tests in the web industries for products as diverse as tissue and steel and everything in between. This test instrument can often yield other useful material properties with a bit of setup and software cleverness. The grab tensile is more common in the textile industry, and we had plenty of not so good words to say about that test in Web201.69h. The tensile is so well covered in the literature that we only need to point to some references, such as our must-have 750-page Web Handling Handbook as a starting point. Still, well covered does not mean well understood, as we will see. Though tensile test instrumentation itself can be pricey, the tensile test is easy enough to perform. There are many motivations for tensile testing, some good and some maybe not so good. Perhaps the most common by far is that we measure tensile tests because Grandpa measured it. However, just because Grandpa did it does not necessarily mean that we should do it too. A much more concrete motivation is contractual agreements. If you or your customer have written into their grade specification or purchase agreements any mention of tensile testing, then you had better do it too, even if it does not necessarily have any other practical or trustworthy application. Many of the other motivations for tensile testing often make assumptions that are not necessarily checked. These include using tensile testing as a proxy for more tangible concerns, such as monitoring variability, customer satisfaction, and web breaks, as just a few examples. In contrast, web handlers have quite strong motivations for tensile testing. That is, it can predict optimum tensioning of materials going through machines as diverse as tissue and steel and everything in between. There's a whole body of analytical and experimental science that is covered in Chapter 4 of our must-have 750-page Web Handling Handbook, as well as in hundreds and hundreds of other places in the literature. I was a central figure in a horror story that I'm about to share. It involved one of the most common tensile test procedures, using one of the two top names in tensile testing equipment. This took place at a Fortune 500 company who had exceedingly strong statistical departments. I will not reveal the names here so as to protect the guilty. However, this story is not just about tensile testing. It is about testing in general, and one of the many reasons why I subscribe to the Roisum rule of instrumentation. I went to an ordinary test lab to get tensile test results so that I could check on web machine tension settings that were used on a converting machine in that plant. Web handlers know that a good starting point tension is in the range of, say, 10 to 20% of MD strip tensile test in, of course, engineering units. Testing can be time-consuming and often boring. So both the eye and the mind wander looking for something interesting. And I found it. And then some. The green figure on the right shows a proper test specimen geometry. The necked specimen must depart from the grips at the same location that it was prior to elongation. More importantly, for this purpose, the specimen must depart from the grip at a perfect right angle. This is required by mechanics if the specimen is truly fixed at the grips. The yellow figure at the left shows what really happened. The specimen departed at a slight angle. Now, this is something that no one other than perhaps someone familiar with elasticity or finite element would ever notice, because the angle is quite small. But to those with a background, this is a big red flag of misbehavior. Also, brakes should not favor the area near the grips, which was also happening. Best practices indicates that test results where the specimen broke at the grips or near the grips should be discarded. I could not believe what I was seeing, so I asked the technician to run a few more tensile test specimens. They all did the same thing. Now, I knew that this was not just a one-off misbehavior, but rather was something systemic. There is a guideline for troubleshooting that says extraordinary claims require extraordinary proofs. I was about to make a claim that something was totally screwed up about this everyday test. So the next thing I did was to scribe a line on the specimen prior to elongation. After the elongation, the line pulled away from the grips as shown by the red dotted line. This was clearly showing that the specimen was slipping into grips as the tensile test proceeded. So we needed to find out why. There were both plain steel grips and ones that had rubber pads on them. Both styles were warped because the metal segment underneath was warped, as shown in the upper right. Now, when I say warped, it was about the thickness of a human hair. However, with webs that are the thickness of a human hair, bowing and flatness issues on the grips of that size means that the web was not firmly gripped along the entire width of the grips. Still, not believing what I was seeing, I visited another lab nearby and found that all of the sets they had were also warped. This means that the problem was pervasive, at least for that supplier. So as a good citizen, I called the supplier and complained. They were not aware of the problem and thanked me for calling attention to it. We can make 3 well-evidenced conclusions from this event. The first was that the specimens were slipping in the stock grips because they were warped. This had happened for at least 1 decade in perhaps a dozen plants in that company alone. No one, whether test instrument supplier nor test instrument user, was aware of the issue. The second conclusion was at least as important because it had direct knock-on effects. That was, the values for stretch, or strain to failure as it's more formally known, was worthless in terms of accuracy. It also reduced test efficiency due to the not infrequent specimen breaks near the grips, which then needed to be retested. I would like to say that this story had a happy ending, but it did not, at least as far as I know. The first response of the test lab manager was, well, the relative results should still be good. In other words, if one specimen tests higher than another specimen, it might actually have a higher stretch. That is pretty wishful thinking, because the test values have a strong crosstalk with the precise value of the warp of that particular grip in use. Of course, this story is not just about tensile testing. It is about testing and instrumentation in general. In my 40 years of troubleshooting in plants, I have run across hundreds of horror stories of roughly similar nature, that instruments are not necessarily reading reality. Some of these were at least as serious and at least as systemic as the story shared here. The bottom line is this: don't trust instruments until someone checks them out thoroughly to begin with, and then cross-checks them regularly. There are 4 starting points for more detailed descriptions of instrumentations used in web handling. The first is my Web401 troubleshooting series on this all web handling channel of YouTube. Please subscribe below. For a more complete discussion, you can see my Critical Thinking and Converting book by Tappy Press. The third is the must-have 750-page Web Handling Handbook, written by myself, Tim Walker, and Dylan Jones. Last but not least is my award-winning and trademarked Web 101 class that has been taken by about 5,000 people, just like you. Here, you will learn how to use material properties and the laws of physics to understand web behavior and web misbehavior. Thank you so very much for joining me in this Measurement Miasma mini-series. Stay tuned for the next clip where we will discuss secrets of a level product and process. There you will find most serious issues with another one of the most common and most important web quality measurements: thickness profile. If you have a topic you would like to hear about, let me know in the comment section below. If you found anything interesting or useful here, please like and share and subscribe. See you next time.